Okay, so last lecture on constraint programming. This is the square lecture. So we're going to see a lot of problems on squares, magic squares, perfect square. It's a really interesting thing. We are in search again, okay? So trying to see various techniques for doing search. And once again, this is just introduction, okay? So there are a lot more to this area. It's a very active research area, but I'm touching upon a number of topics that are interesting, okay? So we're going to try with value variable, labeling. Most people are going to do variable value labeling, and at some point, it's boring. So what we're going to do is something very different, which is called value variable labeling. So instead of choosing the variable and then assigning the value, we want to look at the problem in a completely different fashion, right? We want to look at the value and then choose a variable to which to assign that value, okay? So we take a value and then we take the variables to which we want to assign that value. Okay? Now you're going to say, this is crazy, right? So this makes absolutely no sense. Okay? But in practice, there are a lot of applications where you know that a particular value has to be assigned. Okay? This typically happens in scheduling. This also happens in timetabling problems where you know that a class has to be assigned to something, a professor has to be assigned to a particular class, and so on. Or in scheduling, you know that a task has to start at a particular point in time. Okay? So it's very useful in many applications. Okay, so but I want to illustrate that with a really nice example. I'm going to get out of the way. Okay, so what you see on the screen are 21 different squares. Okay, they are squares and they all have a different size. Hello. Okay, so I'm on the other side. Okay, and so the goal here is to look at all these squares. Okay, and make them into one big square. Okay, so we have to pack them and arrange them in such a way that we make this big square. Okay, now I'm assuming that you are completely bored at this point. You can't sleep. I'll let you look at this thing and you can spend the next 20 minutes trying to put all these squares in that big square. It's very interesting. Okay, so 20 minutes. Okay, so and what I want, so this is one of the solutions. Okay, I won't let you look at it very quickly, won't let you look at it very long because I want you to be able to solve this puzzle if you can't sleep, right? So if we try to solve that using a constraint program, we have first to decide what the decision variables are going to be, okay? And they're going to be the x and y coordinate of every one of these squares, okay? The bottom left corner of one of every square. It could be the top right corner if you want, but you have to choose one, and that's where you're going to basically, that's what the convention that you're going to use. In our particular case, we take the bottom left corner, and that's the position of the square. As soon as you know these two, the x and y coordinate of that corner, you know where the square is. Okay, what are going to be the constraints? There are two types of constraints. The first one is easy. The squares have to fit in the small squares have to fit in the bigger square. And then obviously the square can't overlap. You want to make this big square, but you can't have the squares overlap. Okay? Now there are also some redundant constraints. Okay, so I won't go into all the details, but I want to give you the intuition. So here is the intuition. Okay, so if you look at that vertical line here, okay, so that vertical line corresponds to an x coordinate. Okay, and it's basically intersecting a number of squares. So what you want to be sure is essentially that the sum of the sizes of the square that this line is intersecting is equal to the size of the big square. Okay, so that's a redundant constraint that you have. Okay, and this is essentially a model. It's a very wide model. Okay, expressing everything that I've told you about. Okay, so you have the decision variables, which are the x and y coordinates there for every one of the square. Okay, then you have essentially a set of easy constraints there that are basically telling you that the square have to fit into large square. And then you have two types of constraints that I mentioned. These are the redundant constraints, and they are basically reified constraints. For a particular position P, you are going to look at the square which are basically intersecting with that particular, actually intersecting with P, okay, containing P in a sense, and making sure that the size is the side of the big square. So this is a reified constraints. And then you have the overlap constraint, which are easy to state. Essentially, if you have two squares, you have to make sure that the square, one of the square is on the left, the right, on top, or below the other square. Okay, so once again, it's a big disjunction of the various cases. Okay, so but this is just a statement of the problem. What is interesting here is the value variable labeling. Why do we do that? Why don't we just place the various squares at this different position? And the basic idea here is that we know that we have to fill this big square, and it's going to be completely filled. Okay, so there is no empty space in that particular big square at the end. So we know that every time there is an empty space, we have to place a particular square over there. Okay, and that's why we are using a value labeling here. okay? Value variable labeling. Because as soon as there is an empty space, I know that I have to choose one particular square to be put there. And therefore, I can just look at the square and choose which one is going to be placed there, okay? Visually, okay? So look at this. I place one square, I place another square. I know for sure that one square will have to be placed there. Which one is it going to be, okay? And I place another one and then a tiny one there. Oh, there is an empty space there, which is the square that I'm going to have to place there. And that's the basic idea behind the value labeling procedure that I'm going to show you. Now, you can write very complex one or you can write very simple one. I'm going to show you a very simple one, which works almost as well as the most complicated the most complicated ones, but it's actually very simple to state. So that's what I want to show you. Okay, so what we are going to do. Essentially what we are going to do is that we're going to take this vertical slice, let's say P, okay? And then we are going to decide for all the square, do I place P there or not, okay? So it's very, very simple, okay? I take all the x coordinate P and I decide whether I place, which squares do I place there. And then I move to the next coordinate, I do the same and the same and the same and the same. And then I do the same for the y and the y and the y, and that's what I do. Okay, so this is the search procedure. Okay, very simple. I told you we could do a more complicated one, but it doesn't bring very much benefit in practice. So I'll take basically all the x coordinates. Okay, and then I iterate for all the squares that you see there, and then I decide. Do I place that particular square at that position or not? Okay, and most of the time it's going to be not, but essentially that's all I have to do. Okay, so these are for the x coordinate, and the bottom here is for the y coordinate. That's all I have to do in this particular case. Okay, so it's a value variable labeling. I take a value and I decide, do I place it? Is this square being placed at that particular position or not? Okay, and this is very, very effective on this particular application. Okay, so this is basically what you're seeing now is variable value labeling and value variable labeling. Okay, what I'm going to talk about now is a very completely different way of actually branching, which is called domain splitting. And I'm going to use another square example, which is called the magic square example. Okay, so essentially you have the number. Okay, you have a set of numbers to be placed in a particular square. All the numbers have to be different, and then all the rows, columns, and diagonals have to sum, when you look at these numbers, have to sum to the exact same number, okay? So this is a magic square of side 3, okay? So you see the value 2 and 9 and 4, okay? So if you look at the sum of every one of these lines, okay? So this is one of these rows, okay? It's going to sum to, in this particular case, 15. So all these rows are going to sum to 15. You're going to look at all the columns now. They are also going to sum to 15. And the two diagonals are also going to solve to 15. So you see 2, 5, and 8 there. That's basically 15. And the other diagonal is also going to sum to 15. That's what you have to do. Okay? So basically, if you have a square, 3 by 3, okay, you know that you have to place a number between 1 and 9 in this square, such that the sum of all the rows, the sum of all the columns, the sum of all the rows, and the sum of the two diagonals are equal to 15 in this particular case. Okay? Now this seems easy enough, right? So we could do that by hand. Okay? What I want you to think about is, can you do that for a square or 11 by 11. So we are going to place essentially 121 number in this particular square, and we have to make sure that all the rows, all the columns, and all the two diagonals are going to sum to the same value. Okay? So how do you do that? Okay? Now actually, what you should really think is that can you actually solve that for a square which is 1,000,000 by 1,000,000? Okay? And this can be done. Okay? This can be actually done efficiently. But for today, let's just think about 11 by 11. Okay? Now the key question here is that when you try to do that, which variable are you going to assign? So do you want really to assign? So this is a solution to this one. So one of the things that we need to think about is how you are going to do the search for this particular example. Okay? But before thinking about this, let's just think about what the statement of the problem here. Okay? So what you see there are basically the decision variable s. Okay? That basically means for every square, you have to decide which value you give. Okay? The value in this particular case are going to be between, if the square is of size 11 by 11, is going to be 11 squares, so 121. Okay? So that's the domain of the variables. And then what you see here are the various constraints, okay? All the rows and the columns and the two diagonals have to sum to the same value t that you can easily pre-compute at the beginning. Okay, and then you have also to make sure, of course, that all the numbers are all the slots inside the square are different. So you assign different values to every one of the slots. So that's the statement of the problem, which is easy enough. What is, of course, the most interesting part is how do you actually do the search? Okay. So one of the things you could do is you could select one of these squares. Okay, this one looks nice. Okay, well, let's start there, and you could decide, I'm going to assign a value to that particular variable there. Okay. But essentially, when you look at this thing, right, so this is a big square, right? You are going to take this variable and assign it a value, okay? But this is essentially completely random at this point, right? So you have absolutely no clue what you're doing, right? So you're going to take a particular variable, take a value, but it's a completely random guess. And in addition to being a very random guess, it's going to be a very strong commitment. You are basically saying, I want that particular variable to be that value, okay? So can we do something which is like a weaker commitment? Okay, and that's what we're going to do. So domain splitting is basically you're going to select a variable, and instead of assigning a particular value, you're going to say, ooh, wait a minute, right? So I don't want to make a big decision here, right? So what I'm going to say is that I'm going to, see if I can actually find a solution if I assign, a value which is in the upper half of my domain or the bottom half of my domain. Okay, so you split the domain in two, and you say, okay, so I'm going to try to place this particular value. I'm going to basically assume that that variable is in the upper domain or the lower domain of its actual domain. Okay, and this is what we can do, and this is a search procedure expressing you that. Once again, you are going to loop until you assign all the variables. Okay, at every one you select a variable using the first principle, so a variable which is very tough to actually assign. And what this is doing here is not assigning a particular value to that variable. What you do is you take the midpoint in the domain, that's the mid value that you see there, okay? And then you basically say, oh, the variable has to be smaller than the mid value or greater than the mid value. So the choice that you do here, okay, is much weaker. You are basically assuming that the variable is inside a set of value, but you haven't specified which one. So it's a much weaker commitment. And since we have absolutely no clue in this particular problem what to do, this is going to be a very effective strategy in this particular example. Okay? So you're going to say, oh yeah, but this is a puzzle. No, this strategy is actually extremely good for very hard car sequencing problems. So remember, we saw that before a couple of lectures ago. So you have cars on an assembly line. Every one of these beautiful cars, okay, is basically requiring some options, moonroof or leather seats and things like this. Now, to actually put these options on the cars, you have these production units, which are basically putting this thing as the car is moving in front of the production unit. And therefore, you have to be careful. You have to sequence the car in such a way that you have the time to actually put the various options on every one as the car is moving in front of the production unit. Okay? So we had, the first time I've shown you that, essentially a simple variable value strategy, okay, which for a lot of instances is actually working pretty nicely. But on some of the very hard instances and some of the instances which are actually infeasible, it's not the best strategy that you could use. And one of the things that you have to recognize here is that the options that you see here, okay, they have different strengths. Okay, some of them are really tight. Okay, so let's say the first two here are really tight. There is essentially no slack. It's very difficult to insert a new car with that particular option. And when you look at some of the other options that you see there, okay, especially the fourth option, for instance, it's a very loose option in a sense. There are many ways you could actually place other cars. There are plenty of areas where you see essentially no cars being placed. Okay, so in a sense, when you are trying to solve these problems, what you want to do, and this is once again the first field principle, is focus on the options that are really, really difficult. Okay, but once again, you don't really care about the various types of cars. What you really care about is, do I place a car in this particular slot requiring that option or not? Okay, so what you want is not reasoning about the different types of car. You want to reason about the various options, okay? And you want to focus first on the options that are very difficult. And then you decide, if you place a car requesting that option, okay, in that particular slot. But you are not actually placing a car. You are saying, oh, there will be a car in that particular slot with that option. But I don't want to commit to which car at this point. Okay? So, and this is the key idea. What you are focusing on are the options, and first the options that are really difficult. Okay? And so in a sense, the way to do this is very natural. Okay, so what you do is that you do a search procedure which iterates over the options. Okay, we are not iterating over the various types of car. We are looking at the various options, and then for every line of the assembly, every slot of the assembly line, we are deciding if that particular slot in the assembly line is taking the option. That's the first. That's the first choice that you can make there, or it's not taking the option. Okay? So why does it work? Because you look at every one of the options, and for every one of the slots in the assembly line, you're going to decide, do I take that option or not? Okay? You're not deciding the car, but then you take the next option, you do the same thing. And so at the end of the day, what you are going to do is for every one of these things, you are going to choose very specific configuration, because essentially the other constraints are forcing you to choose between which they are basically enforcing the type of car you have to produce. Okay, so very interesting here. What you do is essentially domain splitting. Every time you make a choice here, you are basically splitting for the particular slot variable the set of cars in two parts. The one that are requiring the options or the one that are not requiring the options. Okay, and you choose first to assign the cars for the options and then the car not taking the options. Okay, so essentially this is once again a domain splitting. You have a much weaker commitment. The only thing that you're doing is deciding whether you have that option for that particular slot or not. Okay, very effective on some of the most difficult car sequencing instances, especially when you want to prove infeasibility. Okay, so far we have seen a lot of different things. Okay, variable value symmetry, value variable symmetry. Okay, we have seen that we can use the first field principle by using feasibility information and sometimes using the objective function. And we have seen that in some instances, okay, we want to do weaker commitment and new domain splitting. What I want to do now is come back to, I promised you that, come back to symmetry breaking and look at how we can actually break symmetry breaking, not by using constraints, but during the search. Okay, and you will see why this is important. Okay, and we're going to go back to this scene allocation problem, right? So these beautiful, these beautiful people, George and Julia and Clive. I like Clive a lot. So he was almost, James Bond, or maybe that was just a marketing, ploy that he had. But he would have been a really great James Bond. Anyway. Dan Craig is a great James Bond too. But anyway, so I'm getting ahead of myself here. So what we are trying to do is shoot these beautiful movies, okay? And the actor plays in different scenes. And remember, they were paid by the scene that they play with. And they were not paid by the scene they play with. They were paid by the number of days that they were on the set, okay? And we had a constraint on the number of scenes that you can shoot every day. So you can shoot on at most case scenes every day. And the objective was obviously to minimize the cost. And one of the ways to do that is basically make sure that the actors, when they spend a day on the cast, are basically shooting as many scenes as possible. Now, there were a lot of symmetries on this particular problem. Do you remember? Okay, so the symmetries were about the various days, right? So the days at the beginning were all interchangeable. Monday and Tuesday, there were no difference for these actors. Okay, so the way we eliminated those symmetries by putting constraints. Okay, so the first scene that we wanted to assign, okay, the things what we said is that it was day one. It could be only assigned to day one because at that point all the days were the same. For the second scene that we were considering, we were basically saying, okay, so that scene can be assigned to day one. That's where scene one has been allocated, or a new day, which is basically day two, because all the other days are the same. At this point, are essentially interchangeable. And so in a general fashion, when you look at scene I, you were basically looking at the day that were assigned before plus a new day, and that's what this beautiful formula was telling you. And so what we did was, doing this nice model, and then you had these symmetry breaking constraints, where you were basically saying that scene one is allocated to one, and then all the other scenes were allocating to the values assigned to the previous scene plus a new one. Okay, and so you were basically, what we were doing was basically putting all these constraints inside the model. Okay, so they are symmetry breaking constraints. They were getting rid of the symmetries in the particular instant, in the particular problem, and these symmetries were basically taken care of by putting these additional constraints. Okay, now when you think about this and you think about search, these constraints had a dramatic effect on search, right? So if you use the first field principle, what's going to happen? Okay? Essentially, these constraints are going to dictate mostly the way you are basically doing search. Why? Because the first scene is already allocating. There is no choice. Then you look at the second scene, okay, which is, in the particular order in which we stated the problem, right? So that second scene is a domain of 2. The third scene is at most a domain of 3. The fourth scene at most a domain of 4. So essentially, when you use the first field principle, you are basically, by stating these constraints, you are basically choosing the order in which you have to assign the variable. Is that good? Well, sometimes yes, sometimes no. But in this particular case, it essentially prevents you from using any kind of sophisticated heuristic, because it's basically, you are basically constrained by these constraints that are basically reducing the domain of the variables. So can we avoid it? So there is an interference between the symmetry breaking constraints and the search heuristic that you could use. If you wanted, for instance, to use a heuristic that was using the first field principle, the smallest domain, and then let's say the scenes that are the most expensive one first, you were not doing that, because essentially these symmetry breaking constraints were imposing a particular order. So can we actually get rid of this? And the answer is yes. And what we have to do is take these symmetry breaking constraints and not impose them in the model, but kind of introduce them dynamically during the search. So we're going to impose essentially the same symmetry breaking constraints, but dynamically during the search. Okay? So in a sense, the big difference between imposing them inside the model and imposing them during the search is that the ordering is going to be different, and it's going to be discovered incrementally by looking at the variables which are the most difficult to assign. Okay? So in a sense, what we're going to do, the search heuristic is going to be choosing the next scene, and that next scene will take the one which has the smallest domain to implement the first field principle, and in case of tie, we'll take the most expensive scene. Why would we do that? Because those actors, if there are many of these actors that are very expensive, we want to start with these scenes, because essentially, that will increase directly the value of the objective function. If we place that particular scene and some of the actors, this is a new day for them or this is not a new day for them, that will have a dramatic effect on the objective function. So the heuristic is going to take the scenes which have the smallest domain, and in case of ties, we're going to break that by looking at a scene which is expensive, which basically means the scene which contains a lot of actors whose fees are very high. Okay? So now, essentially, we have to choose what we are going to do. Okay? So we have to break the symmetries during the search. So when we take a scene like this, we'll have to decide which days we will consider for that particular scene. And once again, we're going to do exactly the same trick as we did for the static constraint. We're going to take the existing days plus 1, a new one. Okay? But now we are not imposing these constraints inside the model, right? So we are imposing them during the search. Okay? So when we label the scene, the only values that we will consider for that particular scene are the values of the days that we have used before plus 1. Okay? And the advantage here is that you essentially break the same symmetries. You break the same symmetries. Sometimes you use these constraints a little bit later, but they don't interfere with the search heuristic at this point. They don't change your heuristic by putting these constraints dynamically during the search. You don't change the heuristic. Okay? So this is what you can do here. This is essentially the search procedure expressing that. Okay? So what you see here is that when you try the value for a particular variable, you take the existing day that you computed above there. Okay? That's the days that you have already used, and then you take a new one. Okay? So that's how you're going to break the symmetries there. You don't consider all the possible value in the domain of the variables. The only thing that you do is you take the existing days plus a new one. That's the only values that you select for that particular variable. Of course, what you see on top of there is basically selecting the minimum value. So what you do there is you select the scene which has the smallest domain, and then in case of tie, which is the most expensive. Okay, so that you see basically a dynamic ordering there, choosing the one which has the smallest domain, and this is not actually influenced or impacted by the symmetry breaking constraints, and then the one, and in case of ties, the one which is the most expensive. Okay, so once again, this is essentially the same symmetry breaking ID. The difference is that we don't impose them statically in the model. What we do is we actually introduce this constraint dynamically during the search by limiting the set of values that we consider for every one of the variables. Okay, So this is the last technique, though, that I want to talk about, which is randomization and restart. Okay. So we'll come back to this when we talk about large neighborhood search, which is a more sophisticated use of this. But what I'm going to talk about now is very simple, but it can be very powerful for some example. Okay. And so the basic key intuition here is that sometimes there is no obvious search ordering, but the structure of the problem is such that there is one. We just don't know which one it is. Okay. Right, so these are kind of interesting problems where there is a good ordering, but it's very difficult to find it. Okay, so what do you do when you are in a situation like that? You know that there is a good ordering, but you don't know which one. You don't know where it is. So what we're going to do is brute force, right? Completely stupid. What we're going to do is we're going to randomize. Okay, so we're going to randomly generate some ordering. Hopefully, we'll try to find good ones. And then if this doesn't work, if we can't find a solution in a reasonable time, we're just going to restart, generate another ordering, and try to see if we can find a solution with that ordering. Okay. So the key idea is that we try something. If it doesn't work, we stop early, right? So we see, ooh, this is looking really bad, and you try another ordering, and we try to see if we can better with that ordering. Okay. So in a sense, the key idea is to try a variety of random ordering. We execute the search with those ordering. If it doesn't work after a certain time limit or a number limits on the number of failures, you restart the search and you see if with another ordering you can do better. Okay? So this is very useful for this magic square problem, for instance. So when you look at this thing, I told you before, we can assign a value to a variable. We have absolutely no clue we are doing. Even when we do domain splitting, we basically have no clue what we are doing. But on this particular problem, sometimes you have good orderings that are going to make a big difference. Okay? So where do we start? We don't know. So what we're going to do is we're basically going to randomize. Okay? So instead of choosing essentially the variable which has the smallest domain, okay, we're going to select, let's say, one of the three best variables. Okay? One of the three variables which have the smallest domain. Okay? We just randomize the search a little bit. We don't commit to the variable which has the smallest domain. And then we're going to limit the time we spent, and if we exhaust the time limit, we're just going to basically restart the search, possibly by increasing the time limit, such that we improve the chance that we actually find a solution. And this is the only thing that you have to do, okay, to do that. So what you see, in shadow gray over there are basically, the search procedure that I've shown you before, and we are making very, very few changes. One of the changes that you see there is that we are randomizing. Instead of selecting the variable with the smallest domain, we are selecting one of the three variables which have the smallest domain, And then essentially we have this repeat loop, which is basically restarting this search, okay? And we are making sure that we can only search for a certain time limit, okay? And if we failed, finding a solution, when we restart, we increase the time limit. That's all we have to do for actually implementing this, okay? So what we do, basically, we do the search here. It's randomized, so we're going to pick up the variable ordering in a random fashion. If we find a solution, great, okay? If we don't, after a certain time, we restart, we increase the time limit, we re-execute this procedure, which basically means that we're going to find another random ordering for these particular variables, okay? And we're going to search with that particular random ordering, and if we find a solution, great. Otherwise, we'll redo this thing until we find a particular solution. Okay, so this is kind of brute force. Okay, once again, it's combining all the techniques that we have seen before. We can put anything in there, but on top of this, we are basically introducing this restart and randomization, which can be, very powerful for some classes of application. Okay, so at this point, we have basically covered all the lectures on constraint programming. The next set of lectures are going to look at local search and look at some of the same problems using a different technology. Thank you very much.